So, good evening. Is it audible clearly? Yeah, great. So, let us start. So, in the vector calculus, we discussed about the gradient. So, which is nothing but the three-dimensional derivative of a random function phi, right? Now, here, one of the applications of the gradient is to find out the unit normal vector. Now, exactly in the similar manner, so there are other varieties of this del operator, that is the divergence and the curl. Right? So, this divergence is nothing but it is, so if there is a closed volume, in that closed volume, if there is a continuous generation of some kind of field, maybe an electric field, maybe a magnetic field, or maybe a fluid field. So, it is easy to explain the visible part. So, the visible part is the fluid field, right? Now, if there is a closed volume, from this closed volume, if there is a continuous generation of water, so this water is trying to travel in all the directions from this particular sphere, right? So here there is a continuous generation, then it is going to distribute in all the directions, right? Now, how much quantity of the fluid that is getting generated from here, it is going to diverge from this particular volume, right? Now, the volume that is getting generated and then going out of this particular closed surface is called the divergence. So, divergence is the volume or the field that is getting diverged per unit volume. Is called divergence. So, in fact, this can be easily understood as the ability to expand, we call as divergence. So, per unit volume, how much it is getting expanded is called the divergence of that particular volume. So, suppose actually, let us imagine this way, this room is completely filled up with some kind of sponge. Now, that sponge, if you take it, if you allow to, suppose you try to compress it and keep it together. Now, just leave that. Then actually, it is going to expand like this. This expansion per unit volume is called the divergence of that particular particle or that particular sponge material. So, divergence is nothing but the ability to expand per unit volume. So, that's what is the divergence. Now, if you calculate for the entire volume, there is a total divergence over this complete volume. Got it? So, this is, in fact, it is very much popular in case of fluid dynamics, where we are going to use this particular phenomena of divergence as the continuity equation. The continuity equation is nothing but, suppose if there is a continuous generation of the fluid within this particular room, then this water that is getting generated continuously, it has to travel through the surfaces of this particular wall in all the directions. Now, how much quantity of water that is crossing these walls is exactly equal to the quantity of water that is getting generated within this particular room. Now, this is what we call as the continuity equation, or most popularly in physics, what we learn this as the law of conservation of mass, right? Law of conservation of mass is otherwise called as the continuity equation in case of fluid dynamics. Now, that is going to be proved as, suppose if this field fluid, so this is fluid field, let us say F, then del dot F equal to 0 is nothing but the continuity equation. So, continuity equation. So, here del dot F is equal to 0 is nothing but incompressible fluid. Incompressible fluid. That means you cannot compress that. So, here the water actually, suppose if you are not able to compress it, or if you are not able to expand the water, then the continuity equation has to be satisfied as del dot F is equal to 0. No compression, no expansion. Hence, there is no extra generation or extra inhalation of the water there. So, that's what we call as the continuity equation, which is given as del dot F is equal to 0, which is nothing but the divergence of the function F is 0. So, this is I dou by dou x plus j dou by dou y plus k dou by dou z operated on the vector field F with the dot product. So this F is termed as Fx into I plus Fy into j plus Fz into k. Now this divergence is nothing but dou Fx by dou x plus dou Fy by dou y plus dou Fz by dou z. So this is the divergence del dot F. This is how we calculate for any vector field F. Got it? Understood? Any questions on this? Yeah, you can take. So this is actually independent of the coordinate system. So here actually what we have discussed is the Cartesian coordinate system where the divergence, this way understanding the divergence is very easy. But the analysis purpose, if you want to take it on the cylindrical coordinate system or the spherical coordinate system, this will be a little bit difficult to understand. That also I am going to discuss. Don't worry about it. Got it? So first understand the concept. Yeah. So this one, the next one is the curl. So curl is nothing but the rotational component. So curl is the rotational component of the field. Suppose if this field is generating a rotational component, that means let us say if the water is continuously flowing. So the continuous flow of water, somewhere actually you can see there are certain curls that are generated. So is there any curls that are present that you are going to learn or that you are going to understand with the help of del cross on it. So del cross is nothing but, so this is del cross if you apply on the vector q, where q is usually the velocity vector. So this is velocity vector field. If you apply del cross on this, del cross q is called the curl q, right? So this will give a quantity which represents the rotational component of the fluid field. So how much it is tend to rotate, that is the quantity this is going to give it. So that's what we call as the curl. Suppose if the curl equal to 0, then we say the field is solenoidal. So if del cross q is equal to 0, then q is called as irrotational field. Similarly, if del dot q equal to 0, then q is called as solenoidal field. If del dot q is positive, suppose if it is positive, then the field is expandable. If del dot q is negative, then the field is compressible. If del dot q is 0, then the field is incompressible. Right? Or solenoidal field. Got it? So this is how actually we classify this. So this del cross q is equal to 0 means irrotational field where the fluid is continuously passing this way. Suppose if it is positive, then actually you may assume that in one direction it is trying to rotate. Usually we take as anti-clockwise directional rotation as the positive, and the clockwise directional rotation of the fluid field is taken as the negative. But so there is a rotational component. If there is no rotational component, then del cross q is equal to 0. So as I explained in the previous classes, where if this is 0, q can be expressed as a function of some other quantity, that is del phi. So q can be expressed as del phi in case if del cross q is equal to 0. So this has got lot of applications I explained in the introductory class. Got it? So in total, hope you understood what is divergence and what is curl and what is gradient. Got it or not? Do you have any questions on this? Any questions on this? Okay. Note down this. Noted? Okay. Now, other two concepts what you need to understand to apply the divergence theorem or the Stokes theorem or the Green's theorem, that is, you need to understand how to do a line integral and a surface integral. Now, a line integral is nothing but, so solenoidal field means actually, so this is del cross q, del dot q is equal to 0, right? Means, so in other words, actually we call this as irrotational. So in other words, we call this as solenoidal field, that is incompressible fluid. That means no change. So that is an English meaning, I think. Where does curl finds applications? So curl finds actually a lot of applications in case of fields, right? So you have applications in electromagnetics and you have applications in fluids, right? So in fluids actually you wanted to identify the curly flow. Like actually suppose if the fluid is rotating like this, then with what velocity it is rotating, with what angular velocity it is rotating, how much force it can withstand. So when we are designing the dams, right? So these factors needs to be considered. There actually we have the applications of the cross product of Q. Got it or not? Del cross Q. So in the electromagnetics also, so when the particle is moving in the presence of electric field, the path traveled by that particular particle, suppose if the electron is moving in the presence of magnetic field, then the path that is going to be traced by that particle, so is getting calculated with the help of the cross products only there. Got it, Deepak? Yeah. It has got a lot of applications. Almost every engineering application finds the application of this vector calculus. So without having vector calculus, I don't think so. You cannot imagine engineering at all. So everything is built with vector calculus mostly. Even the electromagnetics. So that's what we learn in case of physics optics, right? So we proved that is with the help of Maxwell's equations. So the light is an electromagnetic wave. So there also it was proved from the fact of this vector calculus with the divergence and the curl equations. Only the manipulation of these. Got it? It has got many applications. You cannot imagine the scope of this particular subject. Got it? And then the line integral. So line integral actually, you can think of a single application or the simple application wherein if you want to find out the potential in the presence of electric field, so you will be finding out by calculating the work done in moving a particle in a specific direction. Now that work done when you want to calculate the specific requirement, that's what you are going to trace there is, suppose this is the path of travel of the particle under the presence of the electric field like this. So this is the electric field and the particle has to move from here to here. So tracing this path. So this path is getting traced by the particle. Now actually you wanted to calculate how much work it is done. how much work we need to do on this particular particle while moving from here to there. Now, here the problem is the particle is trying to move in this particular path, but the electric field is present in a specific angle like this. Now, then if you want to move in this particular direction, so this is the elementary change in the displacement we call as dr. So dr is the length of the particle. So length of the path, an elemental path we have considered here. So this is the electric field direction. Now the component of the work that you have to do is, that is F dot dr is the work. So F dot dr is nothing but the elementary work you have to do under the presence of this force field F when it is moved for an elemental distance of dr like this. Got it or not? So force into displacement is nothing but the work. Now this work while moving from here to there, how much it is done? So that is nothing but W is equal to integral F dot dr over the complete length of L, and this is called as the line integral. Got it? So why it is coming into picture here, it is F dot dr. If you notice, when you are moving in this direction, you have to do the work against the force field. That means force is trying to move in that direction, but we wanted to move in a direction which is opposite to the force with certain angle. But here actually if you notice, the force is moving in this direction. I am also wanted to move in this particular direction. That means both together will aid here. In this direction, both together will oppose one another. So that means there is a negative work here, there will be a positive work here, right? So negative work and the positive work. Now all such kind of negative work and positive works, if you add it together, finally you will be reaching at this point. Now the sum of, or the algebraic sum of all the individual works of every elemental movement will be given by this particular equation, which is nothing but F dot dr over the contour C or over the length L. Got it? And this is what we call as the line integral. Understood? Any questions on this line integral? I think we cannot take the initial and final position because see this work is right. So work is nothing but the positional dependent. But for calculating the work, this is the methodology you have to adapt it, right? Finally, if you want to take only the positional change, I think it will not give appropriate answer. Got it or not? Here the problem that comes is at every place actually this dr is getting changed. That means what you are trying to say is you directly join a line here, and then this force field is not a specific direction, right? So here the problem that is coming here, it is if it is a single force, that is fine, but here there are infinite force lines are there. Everywhere it is dependent on the position. The direction of the force is dependent on the position where you wanted to calculate it. Now if it is a single force, then directly you will be able to calculate with the help of taking the displacement vector and the force vector in a specific direction. But here, suppose if the field is this way here and this way here and this way here, then how do you do that? There the application of this vector calculus coming into picture as line integral. Understood, Deepak? Got it? Okay. So similarly, the surface integral. Okay. Yeah. So will the work be, so may not be 0? What you are saying is it not 0? See this, if there is a equipotential surface, if you are moving on the equipotential surface like this, then actually if you come back, then actually it is going to be 0. But actually here the assumption is equipotential surface. Now actually there are different directions actually we are assuming. Now the work done is different in every direction. If you take a finite path, right? So definitely it may not be equal. Suppose if there is a north, see this. Suppose you are moving from here to here, like this. Now actually in such cases, then what happens is the force field in one direction it may be more, in another direction it may be less. So that's why you have to do some additional work to reach back to the same. Got it? Yeah. So surface integral. What this surface integral talks about is surface integral. So this surface integral comes into picture when we deal with Gauss divergence theorem, right? So in the Gauss divergence theorem, what happens is, see this, let us say this is a surface. Now in this particular surface, let us say this is a closed surface like this. Whatever the volume that is getting generated here, this has to cross this particular surface and go out, right? In all the directions actually it is going. Now Gauss divergence, by common sense, you will be able to understand the volume of the water that is getting generated here, it has to cross this particular surface. That means, otherwise what we can say is, the volume of the water that is coming out of this particular surface, closed surface, is exactly equal to the change in volume within this particular volume. Got it or not? So that is, as a statement, what he says is, over the closed surface, yes, F dot ds is equal to triple integral over the volume, so F del dot F dV. This is what is Gauss divergence theorem. Now there we have something called this surface integral comes into picture. So first actually we understand what is this surface integral, then we can come back to the Gauss divergence theorem. Now this surface integral is nothing but, suppose if you consider an elemental surface here, and for that particular elemental surface, imagine there is a normal that is coming out of this particular surface. That means the angle between the elemental surface and the outward direction is normal. So this is the angle between them is 90 degrees. That means this is outward normal. Now let us say this force field is coming in some random direction like this. In some random direction the force field is coming out. Usually, right, so if you take an electric field, if there is a charge that is present here, the electric field lines exactly comes perpendicular to the surface. But actually imagine that this is not an electric field. So because of some reason, let us say the force field is in this particular direction. And then this force field is making certain angle with respect to the outward normal theta. Then the quantity of the flux that is coming out is exactly equal to the dot product of these two, that is F dot ds. Now actually I will explain in a better way here. See this, let us say this is a closed pipe. So on this pipe, let us say the fluid is moving in this particular direction. Now when it is moving, let us say I have a slant surface like this with lot of holes in it. So this slant surface is getting crossed by this particular fluid particles like this. Now I have one more surface which is exactly perpendicular to this, and then the same quantity of water that is crossing this slant surface is exactly equal to the quantity of the water that is crossing this perpendicular surface, right? Yes or no? That means what it essentially means for us is, though it is having more surface area, the effective surface area is which is perpendicular to the flow, right? So that means if you take this as the angle, suppose this land surface is here, then let us say if this is the angle, then S cos theta is the perpendicular. So ST is nothing but the perpendicular surface. That means this is the effective surface area. So this has to be decided by the direction of the force field. Let us say if the force field is like this, then actually the perpendicular distance perpendicular direction we are taking. That means F dot ds is nothing but F dot n cap ds. So n cap is unit normal vector, unit outward normal vector. That means suppose if the force field is like this, then the effective component is in the direction of the normal to the surface. That's why ds is nothing but the area. Area usually is a scalar, right? But actually we treat in this particular case as vector because the surface with an associated outward normal, if you treat as a vector, our calculations will be much more simpler, or much more simpler means it has got lot of applications in the name of Gauss divergence theorem. That's why though area is a scalar, in that particular case of the surfaces, so where there are curved surfaces that are present, we treat a scalar with an associated outward normal together as a vector, which is called as the area vector ds bar, because it has got lot of applications if you interpret that way. So that means if the fluid is passing in this particular manner, but the effective quantity of fluid that is coming out is nothing but, so this is F dot ds, which is coming out in the direction. So F dot n cap ds is the outward flow. Understood? Understood or not? So this is the effective surface. This is the effective surface. Got it? Yeah, you can note down this. Done? Note it down? Yeah. So when we do the surface integral over any particular surface, right? So F dot n ds you need to consider, where n is the outward normal. Now based on this we will solve some problems. If f equal to 3xy into I, if f equal to 3xy into I minus y square j, evaluate f dot dr integral, evaluate integral f dot dr where C is the curve in the xy plane, where C is the curve in xy plane y is equal to 2x square from 0, 0 to 1, 2. Y is equal to 2x square from 0, 0 to 1, 2. Can you find out this line integral? This should be straightforward and easy. You should be able to do that. So f dot dr, here actually r is standard format xi plus yj plus zk, which is nothing but the position vector. So this is the position vector. Now dr is nothing but dx into I plus dy into j plus dz into k. So this is the difference vector of the position vector. Now based on this, if you want to find out f dot dr 3xy into I minus y square j dot dr is dx into I plus dy into j plus dz into k. So this is integral over the contour C, where C is y is equal to 2x square. So y is equal to 2x square is nothing but a parabola like this. So this is the parabola, y is equal to 2x square. Now x is varying from, so this curve is varying from 0, 0 to 1, 2. If I take x value only 0 to 1, so x is equal to 0 is this position and x is equal to 1 is this position, then here this is the curve he is talking about. So this is the contour he is interested. So on this contour, x is varied from 0 to 1. and y is varied from x is equal to 0, then y will be 0, and then so this is going to be 2. Yeah, got it? So this point is 1 comma 2. So if you want to find out the integral like this, first you have to do the dot product. This is 3xy into dx, 3xy into dx minus y square into dy. So over the contour C. Now actually here we have got the relation y is equal to 2x square. That means wherever y is there, we can replace 2x square. And then dy you can express in terms of dx. dy by dx is equal to 4x, then dy is equal to 4x dx. So if you replace the corresponding terms here, you can express the entire function in terms of only x and dx. So the whole intention of this line integral is to identify a single variable which will satisfy all the xy or all the variables and all the difference vectors together into a single variable function. So that is the methodology that we adopt to solve any kind of line integrals. Now here everything is changed in terms of x, but the same thing you can even change in terms of y also, you can still get the same answer. Now here 3x into y I can replace as 2x square, and then dx minus y is 2x square whole square, dy I can replace as 4x into dx, and then as everything is converted in terms of x, so the limit value is varying for only x from 0 to 1. So this is integral 0 to 1, and then so 3 into 2, this is 6x cube dx minus 4x power 4 into 4, this is 16 x power 4 into x, this is x power 5 dx. So this integral value you have to put it and finally answer it. So substituting the limits 0 to 1. Got it? So the answer is minus 7 by 6. You can put that. So this is minus 7 by 6. Understood? Okay. Note down on surface integral. Evaluate integral f dot n ds. Evaluate integral f dot n ds over the surface S, where f equal to x square y into I, where f equal to 2x square y into I minus y square j plus 4x z square k minus y square j plus 4x z square k. And S is the closed surface of the region, and S is the closed surface of the region in the first octant bounded by the cylinder, in the first octant bounded by the cylinder y square plus z square is equal to 9, and the planes x is equal to 0, x equal to 2, y is equal to 0 and z is equal to 0. X is equal to 0, x is equal to 2, y is equal to 0 and z is equal to 0. Now try to find out the surface integrals of all the surface. So here actually there is a closed surface what he has given. First you need to identify what is the closed surface. So here the surface what he has given is y square plus z square is equal to 9. That means this is on the yz plane, there is a circle like this. So let us say this is y and this is z. So then it is going to be a circle like this, but only in the first octant. That means this is only 1/4 of the circle, but this circle is coming from the cylinder cut. So that means there is a cylinder that is present along the z axis. Now exactly in the similar manner, so there is a cylinder. So this one, it is like this. So this is, if you notice, this is 1/4 of the cylinder, right? So there is a cut here, there is a cut on the other side. Now vertically and horizontally it was cut and one part is taken out. So this part is at x is equal to 0 here and this is 1, x equal to 2. And then this circle is represented by y square plus z square is equal to 9. This is the surface what he is talking about. Now total how many surfaces that are present? So all the surfaces together are enclosing certain volume. So in that, how many different surfaces that are present? Yeah, so exactly. So there are 5 different surfaces are there. So this is, I call this as surface number 1, and then the bottom one as surface number 2, and then this side is surface number 3, and the other side surface number 4, and then the last one is the curved surface. This is 5. So total 5 different surfaces are there. Now when we calculate the surface integral, there is something called outward unit normal n. So this outward unit normal you have to identify for each of the surface. Now the surface 1 is nothing but this surface. It is in the positive x direction. Then the unit normal is I cap. So this is a unit normal vector for the surface number 1. And similarly for surface number 2, which is on the xy plane going down, this is against the z direction. That means this is minus k cap is the surface number 2 outward normal. Similarly, if you take surface number 3, it is against the positive y direction. That means, so this is on the other side minus j cap. So this is the outward normal of the surface number 3. Surface number 4 is against the x axis. Then it is going to be minus I cap. That is surface number 4. Now surface number 5. So here actually the outward normal is not a fixed direction. So it can go this direction, it can go this direction, or it can go this direction. So outward normal is dependent on the position where you wanted to find the outward normal direction. So for that you have to separately identify the outward unit normal for that particular surface based on the curve given by the equation y square plus z square is equal to 9. So outward normal of the unit of the curved surface so you can cast del phi is equal to del of y square plus z square minus 9. So this is how actually you will be applying. Then dou by dou x is anyway 0, and then this is 2y j plus 2z k. So this is the outward normal. Now unit outward normal will be unit outward normal del phi divided by mod del phi. So this is mod del phi. This is 2y into j plus 2z into k divided by 2y whole square plus 2z whole square under root. So this is the unit outward normal. Then this is going to be 2y into j plus 2z into k divided by, so here 2 square will be 4 and that comes out of the root is going to be 2, and then y square plus z square under root. So here these two will cancel, and then yj plus zk divided by y square plus z square is equal to 9. So square root of 9. So this is going to be y by 3 into y by 3 into j plus z by 3 into k. So this is the unit outward normal which is dependent on the yz position. So the outward normal will be unit outward normal y by 3 into I plus z by 3 into k. So now actually you are able to identify the outward normals for all the 5 different surfaces. Till this point everything is understood? Right? Okay. So once you understand this, then actually you have to calculate the surface integral for all the surfaces separately and add it up together to get the total surface area. Got it? Yeah. So now actually let us take one particular surface. I hope it is noted down. Done? Okay. Now from this, so integral f dot n ds is equal to the sum of all the surfaces so all the 5 different surfaces. Now let us take the plane surface. I take surface number 1. So this is surface number 1 is located at x is equal to 2. So then first you take f dot n ds. So f dot n is nothing but f is 2x square y into I minus y square j plus 4x z square k. Now dot product with, so I cap is the outward normal. So I. So this is going to be 2x square y. So this is 2x square y. And then x value is located at x is equal to 2. So this is f dot n is equal to 2x square y at x is equal to 2. Then it is going to be 8y. So integral over the surface S1 8y, and then ds is nothing but, so this is the area he is talking about. On this area, the variations are along y direction and along z direction. So ds is equal to dy dz. So here dy dz. So this limits, what you need to put it is the limits of this curved surface. So this curved surface, so this side, I'll just shade this. So this is the shaded area, what you need to identify as the limits. So this one integral, so I take y as the constant limits varying from 0 to 2 because, 0 to 3. So this circle is given by y square plus z square is equal to 9. That means this radius is 3. So this is 3. So the radius is coming out to be 3. Then y is varying from 0 to 3. And then the z value is nothing but from bottom to the curved surface. So this curve z square is equal to 9 minus y square under root is the z value, and then you have to take only the positive value because you have only the first octane, that is integral 0 to square root of 3 square minus z square and dx. So y into 8 times of dy dz. Got it? So this is 9 minus y square. Yeah. Z is equal. Now, if you do the integration with respect to z, then this is going to be 8 times of integral 0 to 3, then y into, so z upper limit will be 9 minus y square under root, lower limit will be 0 dy. So this is 8 times of integral 0 to 3 y into, so z value is 9 minus y square under root into dy. Got it? So this integration, so the derivative of the inside value is there at the outside. So this is, if you take this as 4 and then this is 2 and multiply with minus and minus. So minus 4 is out and then minus 2y is here, which is nothing but the derivative of the inside part. So if the derivative is present, then 9 minus y square whole power 1 by 2. So that integral will be 9 minus y square 1 by 2 plus 1, that is 3 by 2 divided by 3 by 2. The outside is minus 4. Got it? So upper limit is 3 and the lower limit is 0. So this value is coming out to be, upper limit if you substitute it is 0, then the lower limit if you substitute it 9. So this is minus 4 times 0 minus, so 9 is nothing but 3 square whole power 3. So that is 3 cube, that is 27. So this is going to be 108. Got it? Understood? This is just finding out the integral value for this particular surface. Note it down. For S1, this is going to be 108 I have got. Done. I need response. I'll just read it. This is just integration substitution, right? So the last row is nothing but minus 4 times of 9 minus y square whole power 3 by 2. Upper limit is 3 and lower limit is 0. I substituted the upper limit 3. Then this is going to be 0. And the lower limit if I substitute as 0, this is 9, which is nothing but 3 square. So 9 power 3 by 2 is coming out to be 27. Then minus 4 times of minus 27 is equal to 108. Understood, Anjali? So one integral value we have got, and another integral values, that is, if you take all other integrals where for surface number 2, then the outward normal is minus k. So minus k, if you take the dot product, this is going to be 4x z square minus. So for the surface number 2, this is minus 4x z square, and then the area is dx dy, and then z value is coming out to be 0. That means this integral value will come out to be 0 because the bottom surface area, that is at z is equal to 0. Similarly, if you take surface number 3, that is, so this side surface against the y. So then double integral over the surface S3. So dot product with minus j. So minus j is coming out to be y square and then dx dz, and then y is equal to 0. So y is equal to 0. This surface is also come out to be 0. So this is 0 and this is 0. And then the surface number 4. So surface number 4 is, that is at x is equal to 0. That means if you take the dot product with the outward normal minus I, this is coming out to be 2x square y minus of surface number S4 minus of 2x square y into dy dz, and then this is at x is equal to 0. It implies this integral is coming out to be 0. Got it? So all the other integrals except for the curved surface, it is coming out to be 0. One integral is coming out as 108, which is this particular surface. Got it? Now the curved surface, actually we have to take a different approach. Note it down. Now we take the curved surface. Now coming to the curved surface, the outward normal is coming out to be, this is y by 3 times of I, z by 3 times of k. Now you have to do the integration over the curved surface ds. So f dot n ds. Now this ds you have to identify it. This ds actually, this is a curved surface, but we don't have a methodology to find out the curved surface integral. For that, what you need to do is you project this particular surface onto the xy plane, and the outward normal you treat as the exactly perpendicularly out, and then the relation that you are going to get it is ds is equal to, or the ds is equal to dx dy divided by outward normal dot k. So this is how actually you need to find it out. So here if you notice, this is n is nothing but ds. So n ds dot, if you notice, if you bring this to this side, n ds k dot. So this is equal to dx dy. I hope you understood this one. K is the outward normal to the dx dy, and n is the outward normal to this particular surface. That means if there is a curved surface like this, and this is the outward normal, and this is the actual normal, so this is k and this is n. Now the angle between them is theta. Now if you take this as the dx dy plane, this is dx dy plane. So dx dy, the surface area is with a normal of k cap, and ds is nothing but with a normal of this one. So the dot product of these two, this is ds. So ds n with a dot product of k, n ds k cap. This is going to be the projected area of this particular surface, right? This ds projected onto the xy plane is going to be dx dy, or ds you can treat as dx dy divided by n dot k. So this is very important to understand while solving the integral values of the surfaces when there are curved surfaces that are present in it. Got it? And rest of the thing is as usual and normal. Now here integral over the surface s phi f dot n. So n is yi by 3 plus zk by 3. Now if you take the dot product, so that is this is j, yeah. So then this is minus y square into y by 3 plus 4x z square into z by 3. So this is f dot n. Then double integral over the surface s, and then this is minus y cube by 3 plus 4x z cube by 3 into, so ds you can replace as dx dy divided by n dot k. N dot k is nothing but z by 3. So this integral you need to be doing. Got it? Understood? Understood? Any questions on this till this point? Okay. So once you understand this, then actually you can express this particular circular surface area as the parametric form. So y square plus z square is equal to 3 square. So y you can replace as y is equal to 3 cos theta, and z is equal to 3 sin theta. You can replace it, and then this is the parametric form. So dy you can replace as, so derivative of 3 cos theta minus sin theta into d theta. Similarly dz also you can replace it and substitute correspondingly at this location. So this is minus y cube, that is 3 sin theta whole cube plus 4 into x into 3 cos theta, so 3 cos theta here, cos theta and 3 sin theta whole cube. So 3 you can take it out, dx dy you can replace in terms of theta, that is 3 sin theta, sorry, we'll simplify this, 3 comes out and this 3 will cancel, and then double integral minus y cube plus 4x z cube into dx dy, and then 1 by z if you take it, this is by z and this is going to be z square. Then you can replace the parametric form, so z is equal to or y is equal to 3 cos theta and then z is equal to 3 sin theta, dy is equal to, so derivative of cos theta is minus sin theta d theta. So you just replace as it is, double integral over the surface S, this is minus y cube is nothing but minus 3 cos theta whole cube by 3 sin theta plus 4x into 3 cos theta, so 3 sin theta whole square, 3 sin theta whole square, and then dx, and then dy you can replace as minus sin theta into d theta. Got it? Understood? Note down this. Okay. So this one, once you find this integral value, what you are going to get it is, so you just need to do the integration for this particular bottom surface. So this bottom surface, the integral limits are going to be, so two different limits, x varying from 0 to 2, this is one, and the y varying from, in the parametric form, so this is the angle with respect to x-axis. So this is going to be, x is varying, so the angle is varying from 0 to pi by 2. So because this angle from x-axis to the y-axis is going to be pi by 2. Now you can identify this. This is minus 27 cos cube theta divided by 3 sin theta plus 4x into 9 sin square theta, and then minus sin theta into d theta into dx. So integral 0 to 2, integral 0 to pi by 2, and then we multiply with minus sin theta, 27 cos cube theta minus 3 sin theta. So 27 cos cube theta minus 12 into 9. 108 sin cube theta. So d theta dx. Got it? So this is how actually you will get it. So this integral you need to apply. This is cos rule you can apply here, and sin rule you can apply here, and then finally what you are going to get it is, I think, 72. Yeah, that's correct, right? So this is 72, and then this integral is coming out to be 72. In total, this is going to be 108 plus 72 is 180. This is the final integral value. So this is a little bit lengthier procedure, but still you will be able to do that. So this is one of the way of methodology for finding out the surface integral this surface integral is going to be used as part of divergence theorem. It has got a lot of applications in fluid dynamics. Got it? Clear? Any questions? Yeah. So do you have any questions? Okay. So if there are no other questions, so I am going to stop the class for today. Yeah. Thank you. Yeah. Good night.